It's going to take us 3 entire weeks to go through how to solve all of second order circuits. But I want to make it clear that the steps that we'll be going through is to first find the initial conditions. And these initial conditions are different than when we found the initial conditions for first order. For first order, no matter what we were asked to find, we found either V sub C for time less than 0 or I sub L for time less than 0. And these were important because if you know what V sub C is for time less than 0, using the principle of voltage continuity across the capacitor, you now knew what V sub C was at 0 plus. This is the same thing as what V sub C was for all time less than 0. Similarly, using current continuity through an inductor, if you knew what the current was for time less than 0, that had to be the same as the current at 0 plus. And then you also found V sub C at time equals infinity, or you found I sub L at time equals infinity. And so those were the two initial conditions you had: V sub C 0 plus, V sub C at infinity, I sub L at 0 plus, I sub L at infinity. And that's different than in second order, where you find what you are asked to find. In other words, if you're asked to find the voltage across a resistor for time t, first order, you'd still find V sub C at 0 plus and V sub C at infinity. But for second order circuits, instead, you're going to find, you found these two things. For second order, you're going to find three things. You're going to find V sub R. So that's different. First order, you'd find V sub C always, even if you're asked to find V sub R. Here, you're going to find V sub R, and you're going to find it actually three different flavors of it. You're going to find V sub R at 0 plus. You're going to find the derivative of V sub R at 0 plus. And then you're going to find V sub R at infinity, non-derivative. Once you find those initial conditions, then you're going to use a plug and chug equation. And that's going to be different too. For first order, your plug and chug equation looked like A plus B e to the minus kt. I mean, yes, it was exactly something like V of infinity plus V0 minus V of infinity times e to the minus t over tau. That's the way we wrote it. But if you do the multiplication out and take a look at the form, it always had this form. For second order, it can have one of three forms. It can have the form of A e to the minus 1 time constant plus a different time constant, or it can look something quite different like this. So notice the difference first is that this has a t multiplied by it, and unlike this version that have two different time constants, this just has one. It's just plain old k for both. And there's a third form too. It could also look like this. This cosine and sine all multiplied by another decaying exponential. So notice that there's only one decaying exponential. Notice there's only one frequency, the same frequency for both sines and cosines. But we've got two variables here. So this is very different than that simpler first order. But one thing that's nice is that with the first order, after you found it, which would always be for V sub C or I sub L, you had to have another step where you then found whatever you're asking for. For second order, it's not like that. You can go directly into finding whatever you're asked to find. Here's a circuit simulation of a second order circuit. I coded it in C#. It's got three components: a resistor, inductor, and a capacitor, and it's got this stepped voltage source I'm plotting the voltage of the source, which is 0 for time less than 0, and then at time 1, it pops up to 1. And let's take a look at what the current is doing in the circuit. So the current in the circuit starts off at 0. It's got to, right? Because there's an inductor here, and inductors always will force current continuity. Since there was no current before 0, there's got to be no current after 0. The inductor looks like water inertia. So as time goes on, it has less and less of an effect. It doesn't like to see changes in current, but the capacitor starts off discharged, and over time, it will distend more and more, resisting that voltage more and more. In fact, if we take a look at the voltage across the capacitor, we can see it slowly rise. Now, you might expect that the voltage across the resistor would never get to be above 1, like it did with the first order circuit. But what's different is that, remember, the inertia through the inductor doesn't like change. So it's going to continue to push current through that capacitor, into that capacitor, charging it up still more. And that capacitance will actually rise above 1 volt, more than it's even being charged to. Then it's going to start to reverse itself. After you've pushed this diaphragm so much, even more than 1 volt, it's going to eventually push back, and you'll get current flowing in the opposite direction. That's over here where it's negative. And that sloshing back of energy back and forth between the inductor and the capacitor will continue back and forth. It's a little bit hard to see, but it's negative here, it's positive here, it's negative here. You can imagine intuitively that you'd have more energy sloshing back and forth if you decrease the resistance. And that's what we see. In fact, although my simulation never lets you take the resistance down to pure 0, if it did let you take the resistance down to pure 0, you'd see energy continuing to slosh back and forth between the inductor. Here you see it at maximum energy in the inductor at these points where it's maximum positive and negative currents, and in the capacitor here where you see it's at maximum positive and negative voltage, and it would continue sloshing and back and forth like that forever. So here's the big difference between first order and second order. There are 3 different equations that control what's going on. Here, when there's not much resistance relative to the amount of capacitance and inductance, you see current and voltage, you see energy sloshing back and forth, and you see sinusoidal waveforms. Sinusoidal waveforms that, because of the resistance, slowly have its energy taken away. And as you increase that resistance more and more, it decays away faster and faster. Now, if that resistance is big enough, it goes from being underdamped, another word for meaning sinusoidal response that you see right beneath in the word right beneath the circuit. It'll go from being underdamped to being critically damped. And at critically damped is at the point where there's no more sinusoidal oscillations. Instead, the current approaches its final value, the voltage approaches its final value as fast as it possibly can without oscillating back and forth. All of a sudden, the equations change from having a sine and a cosine component to just having 2 exponentials, 1 multiplied by t. There's a third region too. If we make this inductor very, very, very small, there's a third region too, besides underdamped, which is sinusoidal, and critically damped, which is when you've got the 2 exponentials, 1 multiplied by a t, and that is overdamped. And an example of overdamped behavior you can see if you increase, and that is overdamped. And as an example of overdamped, if we increase the floppiness of that capacitor, so it takes longer and longer, the capacitor is huge, it takes longer and longer for it to fill up with charge, then you can imagine it's going to take longer and longer for everything to approach its final values. It's less likely to oscillate because we're now being dominated by the value of this capacitor. It's almost looking like a first order circuit. In the limit, if we drop that inductor to close to 0 and make that capacitor really, really large, it would look almost like a first order circuit where we just have a resistor and a capacitor. Now there's 2 different time constants, one controlled by the inductor, which is small, one controlled by the capacitor, which is large. And this is called an overdamped response, where you've got 1 exponential plus another exponential. So that's the intuition, very roughly, about what's going on with the second order circuit, is that it can have three different approaches. It can look like a sinusoidal thing that's oscillating, decaying away. In the critical region, it can be approaching its final value as rapidly as possible without oscillating. And then in its overdamped region shown here, it can be approaching its final value, but not rapidly and not oscillating.